and controls the impedance.
What are the lengths of the different signal traces?
That's another critical one, especially in quad mode where you have the clock, chip select, and 4 data lines all needing to arrive at the receiver more or less simultaneously. You need very tight trace length matching between all these critical signals.
Why is that so important for QSPI?
Because in quad mode, all 4 data bits for a given clock cycle are being transferred at the same time. The clock edge tells the receiver when to sample those 4 bits. If one data trace is significantly longer than the others, its signal will arrive later. This difference in arrival times is called skew. If the skew is too large relative to the clock period and the setup hold times, the receiver might sample 1 or more bits incorrectly, capturing the value from the previous cycle or the next one.
Ouch. How closely do they need to be matched?
It depends on the speed, but at higher frequencies, you might be aiming for skew within just a few millimeters, which translates to maybe tens of picoseconds of timing difference. It gets very tight.
So practically that means careful routing, maybe adding small serpentine wiggles to shorter traces to equalize lengths.
Exactly. And it also strongly encourages placing the QSPI flash chip physically as close as possible to the host MCU or FPGA on the board. Shorter traces inherently have less length mismatch, less signal loss, and pick up less noise. You also want to minimize the use of vias connections between PCB layers on these high-speed lines, as vias introduce impedance discontinuities that can cause reflections and degrade the signal.
So it sounds like achieving that maximum performance listed on the datasheet really requires careful attention to the physical PCB design, not just configuring the controller correctly in software.
That's absolutely right. What ultimately limits the maximum reliable operating frequency in a real system is often a combination of factors. The maximum frequency rating of the flash chip itself, you might see specs like 100 megahertz, 133 megahertz, sometimes higher. The maximum frequency the QSPI controller in your host processor can handle, and crucially, your ability to maintain good signal integrity and meet all the timing requirements on your specific PCB layout. If your board design introduces too much noise or timing skew, you might have to back off the clock speed significantly from the theoretical maximum just to get reliable communication. Sometimes you might need to add series termination resistors near the signal drivers to help manage reflections too.
Okay, so a lot goes into making it work well at speed. Let's switch gears a bit. Where do we actually find QSPI being used in the real world? What are the common applications?
Oh, it's everywhere in modern embedded systems. One of the most fundamental uses is for primary boot and increasingly secure boot. Many microcontrollers have a small internal boot ROM code that runs right on power-up. One of its first jobs is often to initialize the external QSPI interface.
And then load the main code from the QSPI flash.
Exactly. It might load the main bootloader, or in simpler systems, maybe even the entire application code directly from that external QSPI flash. And using XIP here, as we discussed, means the system can start executing that external code much, much faster than if it had to copy everything into RAM first.
Big impact on boot time.
Yeah.
And security.
Yes, it's key for secure boot flows as well. The firmware image stored in the QSPI flash can be digitally signed. The boot ROM, or an early-stage bootloader, can then read the image over QSPI, verify its cryptographic signature using a stored public key, and only proceed to execute it if the signature is valid. This prevents unauthorized or malicious code from running.
So it can ensure authenticity and integrity.
Right. Some more advanced systems even have hardware support for on-the-fly authentication and decryption, or OTFA. The QSPI controller hardware itself can decrypt and/or authenticate the code fetched from the flash in real time as it's being read for XIP execution. This keeps the code secure even while stored in the external flash.
Very cool. So QSPI is enabling both speed and security right from boot time. What else?
It's also widely used for code shadowing. Maybe you have some performance-critical interrupt routines or algorithms that you do want to run from faster internal RAM. You can store them in the QSPI flash and have the bootloader copy just those specific sections into RAM during initialization.
Okay.
And it's absolutely essential for over-the-air OTA firmware updates. The new firmware image is typically downloaded and stored in a separate partition or area of the QSPI flash. Once the download is complete and verified, the bootloader can be instructed to switch over and start booting from the new image location on the next reset.
That seems common in IoT devices?
Yeah.
Does that need careful flash management?
Yes, very careful. You need robust logic to manage the flash sectors, handle potential power failures during the update process, and often employ strategies like A/B partitioning. That means you have 2 distinct slots for the firmware, A and B. You run from A, update B in the background, verify B, then switch to boot from B. If B fails to boot, you can safely roll back to A, QSPI provides the storage, but the update logic is complex software.
Makes sense. And beyond just code and firmware, does QSPI store other kinds of data too?
Oh, yeah. It's commonly used for storing non-volatile configuration data, system logs, maybe calibration parameters. But increasingly, especially in devices with graphical user interfaces, GUIs, it's used to store the UI assets.
Like images, icons, fonts.
Exactly. Images, icons, fonts, maybe even small animations or language translation strings. QSPI's relatively high bandwidth allows the graphics controller or the main CPU to fetch these assets quickly from the flash memory when they're needed to render the screen. This helps make the UI feel much more responsive, even on resource-constrained systems that don't have enough RAM to hold all the assets internally.
So it avoids lag when loading graphics.
Right. While QSPI NOR flash isn't typically used for storing, say, massive video files or huge databases, that's more the domain of eMMC or SD cards, which use NAND flash, it's really well suited for these kinds of UI assets that need quick, often random access during runtime.
Okay. And we see QSPI interfaces mentioned on pretty much every modern microcontroller datasheet these days, don't we?
You really do. All the major MCU vendors heavily rely on it. Think STMicroelectronics with their STM32 families. Many have dedicated QSPI controllers, often memory mapped to addresses like 0 by 900 00000. NXP's processors, like the S32G automotive line, often boot directly from QSPI. Renesa's, Nordic Semiconductor, huge in Bluetooth and IoT, Microchip, Infineon, especially after acquiring Cypress, they all incorporate robust QSPI controllers into their devices.
And it's not just MCUs, right? You mentioned FPGAs earlier. Is it important there too?
Absolutely critical in the FPGA world. For years now, QSPI flash has been the standard way FPGAs load their configuration data, the bit stream that actually defines the hardware logic inside the chip.
Why QSPI for that?
Primarily pin count and efficiency. Loading a large FPGA bitstream used to require older parallel flash chips with tons of pins, making boards complex. QSPI allows that same large configuration file to be streamed into the FPGA much more efficiently using just those 6 or so QSPI pins. It saves board space and cost.
Makes sense.
And beyond just configuration, if the FPGA contains embedded processors, either soft cores like C-Link's AMD's Microblaze or Intel Atera's Neos II, or hardcore processors like the ARM cores in Zinc or Versal devices, those processors also rely heavily on external QSPI flash. They use it for storing their boot code, their application firmware, often using XIP, and for non-volatile data storage, just like an MCU would.
So QSPI is really a fundamental building block across both microcontrollers and FPGAs. Okay, maybe help put QSPI in context. How does it compare to some of the other common interfaces out there?
Sure. We already talked quite a bit about QSPI versus standard SPI, basically. QSPI offers much higher performance, 4x to 8x theoretically, by using more data lines, up to 4 bidirectional versus 1 dedicated in each direction. But it needs slightly more pins, 6 to 8 versus 4, and careful layout at high speeds. Both are typically single slave per chip select line.
Okay. What about comparing it to something like ISC?
IISc is very different. It's much, much slower than QSPI. ISC speeds are usually measured in kilobits per second, maybe up to a few megabits per second in faster modes. QSPI operates in tens or hundreds of megabits, pushing towards gigabits per second.
Big difference.
Huge. ISIS also uses only 2 wires, SDA and SCL, plus ground, and it's inherently a multi-device bus where devices have unique addresses. QSPI needs more wires and typically uses a dedicated chip select for each device. So you'd use ISPIC for low-speed control tasks, reading sensors, configuring simple peripherals. You use QSPI when you need high-speed access to memory, especially for boot, XIP, or large data transfers. They serve very different purposes.
Right tool for the job. Okay, what about eMMC? We hear about that a lot, especially in things like smartphones or more complex embedded systems.
Right. eMMC stands for Embedded Multimedia Card. It's essentially a managed NAND flash memory package combined with a controller, all in one chip using a parallel interface, typically 8 data lines plus clock and command.
So NAND flash, not OR flash like QSPI usually uses.
Correct, and that's the key difference. eMMC, being NAND-based, offers much higher storage capacities, easily tens or hundreds of gigabytes, and generally better performance for large sequential writes. It also has that built-in controller which handles wear leveling, bad block management, and ECC error correction code automatically, making it much easier to integrate with file systems and operating systems.
Sounds pretty good. So why use QSPI and an R then?
The main advantage of QSPI NOR flash is its significantly lower random read latency. It's much faster at fetching small, random chunks of data, like individual instructions for a CPU. This is what makes it suitable for XIP, which eMMC NAND is generally not good at due to its block-oriented nature and higher read latency. QSPI also has a lower pin count than eMMC, 6 versus 10 plus, often lower idle power consumption, and the interface itself is simpler from the host's perspective for basic reads-writes, though the host has to manage erase cycles.
So the choice depends on the primary need.
Exactly. If your system's main requirement is fast code execution directly from non-volatile memory, XIP, and fast boot times with moderate storage capacity, megabytes to maybe a gigabyte or two, QSPI nor flash is usually the better choice. If your primary need is mass storage for large files, media, or a full operating system with a file system, and high sequential write performance is important, then eMMC NAND is likely more appropriate.
Okay. And you mentioned QSPI basically replaced older parallel NOR flash.
Yes, for the most part, in new designs, it has. Legacy parallel NOR flash also offered fast random reads, which made it suitable for XIP in older systems, but it required a very wide parallel address and data bus, easily 30, 40, or even more pins connecting it to the processor.
Wow, that's a lot of pins and routing.
It really was. Made PCBs complex and expensive. Modern high-speed QSPI, especially in quad mode, can deliver comparable or even better read performance than those old parallel NOR chips, but using only 6 or maybe 8 pins. The reduction in pin count, board complexity, and cost is massive, so QSPI has largely taken over that market segment.
What about comparing QSPI NOR to just raw NAND flash? Not the managed eMMC type, but the basic NAND chips.
Raw NAND flash offers the absolute lowest cost per bit and the highest storage densities, but it comes with significant complexity for the host system. Raw NAND is block-oriented. You read and write in pages, kilobytes, within larger blocks, megabytes. You can't easily read or write individual bytes randomly.
Very different from NOR's byte addressability.
Very different. And crucially, the host processor or a dedicated NAND controller have to manage everything. Detecting and mapping out bad blocks, NAND ships with imperfections, performing wear leveling to distribute writes evenly and maximize lifespan, and implementing robust ECC to correct bit errors, which are much more common in NAND and NOR.
So way more software or hardware overhead on the bus side.
Huge overhead. And because of its block access nature and typically higher random read latency, raw NAND is fundamentally unsuitable for XIP. You just can't efficiently run code directly from it. Raw NAND is purely for mass data storage where cost and density are the absolute top priorities, and you have the system resources to manage it properly.
Okay, so QSPI really seems to have carved out this important niche then. It's for fast, byte-addressable random reads, making it ideal for XIP and boot code. It needs moderate capacity, uses a low to moderate pin count, and sits neatly between the low-speed serial interfaces like I-Class C, the high-capacity but complex raw NAND, the managed but less XIP-friendly eMMC, and the pin-hungry legacy parallel NOR.
That's a really good summary of its position in the landscape. It balances those factors: performance, pin count, capacity, ease of random access, XIP capability in a way that makes it incredibly useful for a vast range of embedded applications.
Let's circle back to performance a bit more deeply. Datasheets often give you a theoretical maximum throughput, like that 200 LEPs at 50 megahertz quad we calculated earlier, but you mentioned the real-world performance is often lower. Why exactly is that?
Right. The theoretical maximum is usually calculated very simply.
Yeah.
Just the clock frequency times the number of data lines used, e.g. 133 millihertz 4 bits equals 532 milliPs, or about 66.5 megabytes per second.
Yeah.
But that calculation ignores all the protocol overhead involved in actually getting the data. Before any data bits start transferring, the master has to send the command byte, then the address bytes, 3 or 4 of them, maybe some optional mode bytes depending on the command. That all takes clock cycles.
And then there are those dummy cycles we talked about for reads.
Exactly. Those dummy cycles are wait states clock cycles where the bus is active but no actual user data is being transferred. They add directly to the latency and reduce the effective data rate. There can also be turnaround times required when the bus switches direction, for example, after the master sends the address and before the slave starts sending read data.
Plus, the flash chip itself isn't infinitely fast internally.
Right. The flash memory has its own internal access times, and especially for program and erase operations, the internal physics of modifying the flash cells take a relatively long time, microseconds for programming a page, milliseconds for erasing a sector. During that internal busy time, the QSPI bus might be idle, but no useful work is happening from the perspective of overall throughput. Those internal write erase times often completely dominate the total transaction time compared to the actual bus transfer speed.
And maybe the controller on the host side has limitations too. Like how fast it can fill or empty its data buffers, CFOs, or manage DMA transfers?
Yes, the efficiency of the QSPI controller itself, its FIFOs, how well DMA is integrated, and potentially any congestion if other peripherals are trying to use the same internal bus within the MCU or so at the same time, all those can contribute to achievable throughput being less than the theoretical peak.
So if that theoretical max was, say, 50 megabytes per second,
Yeah.
what might you actually see in a real system for a sustained read?
It depends heavily on the specifics, but maybe you'd achieve something more like 40, 45 Mbps sustained throughput for a large sequential read once you factor in all the overhead. Maybe a bit more, maybe less, depending on the command used, dummy cycles, etc.
Okay, and latency is the other big performance factor, especially critical for XIP performance, right?
Absolutely critical. What really matters for XIP when you have a cache miss is the initial read access latency. That's the total time from the moment the CPU requests a piece of data or an instruction from a QSPI address until the first byte of that data actually arrives back at the CPU.
And that includes...
That includes the time for the QSPI controller to send the command, send the address, wait for all the dummy cycles, plus the flash chip's own internal access time, TCL/QV we mentioned, and any delays getting the data back through the controller to the CPU core.
So that initial hit can be significant.
It can be quite long in terms of CPU clock cycles. While subsequent sequential reads within the same QSPI transaction or using special continuous read modes might be much faster, minimal latency between bytes once the stream starts. That initial latency on a cache miss is often the performance killer for XIP.
Which brings us back to the importance of the CPU cache.
Yes. The overall performance of an XIP system is hugely dependent on the CPU's cache size and efficiency. A cache hit is fast happens at internal CPU speed. A cache miss means the CPU stalls and waits for that full, relatively high latency QSPI read transaction to complete. Without a good cache, or for code that inherently has poor cache locality, XIP performance for complex tasks is generally not great.
And we also have to remember the write and erase latencies are just inherently slow because of the flash physics, right? No matter how fast the QSPI bus runs.
Correct. Speeding up the QSPI clock from 50 millihertz to 100 millihertz won't make the internal millisecond-long sector erase time any faster. Those operations are limited by the flash cell technology itself.
Is there sometimes a trade-off between clock speed and those dummy cycles? Like, does running faster always mean better performance?
That's a really important point. Often, yes, there is a trade-off. As you increase the QSPI clock frequency, the flash memory might need more dummy cycles to have enough internal time to prepare the data before the first clock edge arrives asking for it. So you might increase the clock speed, say from 100 megahertz to 133 megahertz, a 33% increase. But if doing so requires you to add, say, 2 more dummy cycles to every read transaction, those extra wait states can eat into the performance gain. While the clock is faster during the data transfer phase, the increased initial latency due to more dummy cycles might mean the effective throughput gain isn't 33%, maybe it's only 10-15%. Or in some cases, the initial access latency might even slightly increase, which could hurt XIP cache miss performance, even if sustained throughput improves. It's something you have to analyze carefully using the timing specs.
Interesting.
Well, yes and no. The peak active power consumption during a QSPI transaction, read, write, or erase, is generally higher compared to lower speed interfaces or when the device is idle. This is primarily because you're running the clock faster and switching multiple I/O lines simultaneously at that high frequency, which consumes dynamic power. However, QSPI flash devices are also designed with very effective low-power modes. They typically have a standby or idle mode where they draw very little current, maybe tens or hundreds of microamps when the chip select line, CS# is high, inactive. And most also offer an ultra-low-power, deep power down, DPD mode, where they might draw only a few microamps.
But you have to command it into DPD mode and wake it up.
Yes. Entering DPD usually requires sending a specific command, like 0xB9, and exiting requires another command, like 0xAB, release from deep power down, plus a wake-up delay time, TRES, before it's ready for normal operations again. So there's latency involved in using the deepest sleep mode.
So could the race to idle strategy apply here? Finish the high-speed transfer quickly, then immediately go back to a low-power state?
Exactly. That's often a key benefit of using high-speed QSPI. By completing the necessary data transfer, like reading a block of code or assets, much more quickly using quad mode at a high frequency, the system can then put the QSPI flash back into a low-power standby or even deep power down state much sooner. Even though the peak power during the transfer was higher, the duration was much shorter. So the average power consumption of the system over time could actually be lower than if it ran the transfer at a slower speed for a longer duration before sleeping.
Makes sense. So the biggest levers for performance seem to be using the widest bus possible, quad mode, and running the clock frequency as high as the system can reliably handle.
Pretty much. You want to maximize bandwidth by using quad I/O mode whenever possible and push the clock frequency up, but always balanced against the need to maintain signal integrity, configure the correct number of dummy cycles for that frequency, and consider the overall power budget and strategy.
That sums it up well.
Mhm.
All right, to try and wrap all this up, if someone listening is actually working with QSPI in a real product design, what are the most important practical tips or considerations they should keep in mind?
Okay, yeah. Let's summarize some key practical points. First, obviously, is selecting the right QSPI flash device itself. You need to consider the required density, how much storage, the maximum clock frequency it supports, which modes it supports, single, dual, quad, DDR, any specific features needed for XIP or security, its write erase endurance ratings, how many cycles can it handle, the operating voltage, the package type, the temperature range, and of course, vendor support and documentation quality.
Right. Choose your chip wisely. Then you need to configure the controller side correctly on your MCU or FPGA.
Yes, absolutely. Configuring the host QSPI controller properly is crucial. You need to set the clock frequency, SCLK, based on your signal integrity analysis and the flash chip's capabilities. You have to set the correct clock polarity and phase, CPUL, CPHA, to match the flash device again, likely mode 0 or mode 3. Then you need to carefully program the parameters for the specific QSPI commands you intend to use. This includes telling the controller the right opcodes for read, write, erase, status check, etc., the correct number of address bytes to send, 3 or 4, depending on the flash size and mode, the correct number of dummy cycles required for reads at your chosen frequency, and which I/O lines to use for each phase, instruction, address, data. If you're using memory mapped mode for XIP, you need to configure its base address, size, and read parameters within the controller. And think about using FIFOs or DMA effectively if the controller supports them.
Okay, so controller setup is key. Then there's the software driver or HAL that actually uses it.
Exactly. You need solid driver code. A robust initialization sequence right after power up or reset is vital. This sequence should typically read the flash device ID, for example using 0x9F, to confirm communication is working and you have the expected chip. Send the write enable command, 0x06. Then write to the flash's status or configuration registers to explicitly enable quad I/O mode if needed, and set the correct number of dummy cycles for your operating frequency. If you're using a flash larger than 16 MB, you'll likely need to send the command to enter 4-byte address mode here as well.
So get the flash configured properly before you try to do anything else.
Yes. Then your driver needs functions for performing indirect command access for all the operations you need: writes, erases, reading status. And critically, it needs robust status polling logic, especially waiting for that write in progress, WIP, or busy bit to clear after any program or erase command before proceeding. For XIP, the bootloader must perform this QSPI initialization correctly before it jumps to execute code located in the memory-mapped QSPI flash region. Your linker script also needs to be set up correctly to place the XIP code and data in that region. And if you're doing OTA updates, your software needs that complex logic to manage erasing and programming flash segments safely, possibly using dual bank features or A/B partitioning schemes for reliability.
Okay, software is a big piece. And finally, maybe the most challenging part, especially if you're pushing for those higher speeds, the physical PCB layout.
Yes, for high-speed QSPI, the PCB layout is arguably one of the most critical factors for success. As we discussed, you absolutely need tight trace length matching between the clock, SCLK, chip select, CS-shark, and all 4 I/O lines, IO0, IO3. Any significant skew between these signals at high frequencies will cause timing failures. Aim for matching within a few millimeters, which translates to picoseconds of timing skew.
Use controlled impedance traces.
Definitely. Use controlled impedance routing, typically targeting 50 ohms characteristic impedance for all the QSPI signals. Maintain adequate spacing between these traces. That 3x trace width rule is a good starting point to minimize crosstalk. Ensure you have a solid, uninterrupted ground plane directly underneath the QSPI traces to provide a clean return path and help control impedance.
And keep things close.
Yes. Physically place the QSPI flash chip as close as practically possible to the host MCU or FPGA. Shorter traces mean less signal degradation, less potential for skew, and less chance of picking up noise. Minimize the use of vias on the high-speed QSPI lines, as each via introduces an impedance discontinuity that can cause reflections. If you need very high speeds, you might even consider adding series termination resistors, for example 2233 ohms, placed close to the output drivers to help dampen reflections.
Any other layout tips?
Make sure you have adequate pull-up resistors on signals like CS tag to keep it high when inactive, and potentially on IO2, IO3 if they share functions like write, protect, or hold, and might not always be actively driven by the host or slave. And, of course, standard good practice. Place sufficient decoupling capacitors, example 0.1 UF, MAMR 0.01 UF, very close to the power supply pins of both the QSPI flash chip and the host controller to ensure a stable power source during high-speed switching. For really cutting-edge speeds, some advanced controllers even implement features like a loopback clock to help calibrate timing dynamically, but that's getting quite sophisticated.
Wow. Okay, so it's really a whole stack of considerations, isn't it? From selecting the right chip, configuring the controller meticulously, writing robust software drivers and initialization routines, all the way down to the nitty-gritty details of the physical routing on the circuit board.
It truly is a system-level challenge, especially when you're aiming for the higher end of the performance spectrum. But mastering QSPI is what unlocks the ability to run surprisingly complex applications, have rich user interfaces, and boot quickly on the kind of cost-effective microcontrollers and FPGAs that are found in just so many of the electronic devices around us today.
Okay, great. So we've taken this deep dive into QSPI. We started with the basic problem it solves, that need for more speed compared to standard SPI, especially for talking to external flash. We explored its flexible operating modes, single, dual, and quad I/O, and how using more data lines dramatically boosts bandwidth. We looked at how transactions actually work, including those sometimes confusing dummy cycles and the necessary procedures for writes and erases. We spent a good chunk of time on the real game-changing capability, execute in place, or XIP. How it allows code to run directly from flash, which frees up precious RAM and speeds up boot times, while also acknowledging the performance trade-offs, particularly the reliance on caching and the added debugging challenges.
Yeah, XIP is key.
We also touched on managing larger flash capacities using 4-byte addressing, the absolutely critical importance of timing and signal integrity when you push to high frequencies, and saw where QSPI really shines in real-world applications, from bootloaders and OTA updates to storing UI assets across both MCUs and FPGAs. And finally, we put it in context by comparing it to other interfaces like IC, eMMC, and NAND, and pulled out some really practical design tips for making it work reliably.
It really feels like QSPI's role in enabling denser code, richer features, and faster boot times, often on smaller, lower-cost processors, has been a fundamental shift in how embedded systems can be architected.
It definitely seems that way, which I guess raises an important question as we look forward. Given that inherent speed difference between fast internal CPU caches and accessing external QSPI flash, even to highest achievable QSPI speeds, how much further can future system designs really push the limits of cache size and sophistication to try and mask that external memory latency, to make external flash feel almost like internal memory? And conversely, is there a point where the fundamental physics of transferring data reliably over just a few external pins, no matter how fast you clock them or how clever the cache is, becomes an insurmountable barrier to meeting the performance demands of ever more complex embedded applications?